Hi guys, Assalamu alaikum. This is Arif. In this video, we are going to see how we can do rotate right first in Verilog and then in VHDL. So rotate right is that thing once we are going to place the least significant bit at the most significant bit position, and this way we are going to do the rotation. So this is a system Verilog program first, and in this we have defined first of all a module, and its name is rotate right 8 bits. So we are going to implement this using 8 bits of the output and 8 bits of the inputs as well. So we have defined first of all this S as output and then A and B as inputs. Here you can see. Let's skip these lines for the time being, and after that, for the procedural assignment, we are going to make this S output as reg, and then we are going to say always at all values. The star we use for the all signals, or we can define always like this as well. Since we have two inputs A and B, so we can define always like this as well. And after that, we are going to use this branches, which is if else, and we are going to say okay, if the bits from 0 to 2 are 0, then S is going to be equal to A. So B is actually that signal which is going to give us the value by which we are going to rotate this input A. So B is actually from 7 down to 0, which is of 8 bits, but we are going to only use it 3 bits because A is of 8 bits, and in order to do the combinations of A, we only require 3 bits of B. So first 3 bits of B we are going to use only, otherwise we are going to get an error if we are going to use all the bits of B. So remember this, and after that we are going to say inside this if block, if B's first 3 bits are equal to 0, then S is equal to A, and else if we are going to say if B's first 3 bits are 1, that means we are going to rotate A by 1 and put inside the output. So how we are going to do this rotation is we are going to say okay, from 7 to 1 bits we are going to rotate towards the right side, and the least significant bit we are going to place at the most significant bit. So this is A0, we are going to place it or position it at the most significant bit. Then we are going to say else if B2 down to 0 is 2, that means we are going to rotate by 2 bits. So in that case we are going to say okay, place the first two least significant bits at the most significant bit positions. So this way we are going to actually rotate. So 7 to 3 we are going to place at the least significant positions, and 2 to 0 we are going to place at the most significant positions. And this is the way we can do rotation up to all 8 bits from 0 to 7. All 8 bits we are going to cover like this. So this is the last, and we are going to do this rotation and place the values at the output. And as we are going to say make the output equal to CZ, and then we are going to end this always block and then end module. So this is our complete program, the way we can do rotate right. So there are no operators in Verilog or any special functions in Verilog which you can use to do this rotation. So you have to just create this logic by yourself, and then you can do this rotation. So now let's save it, compile it, and actually I can show you the test bench as well. This is a test bench, and in this test bench we are making this output S as wire and the two inputs A and B as rect, the way we usually do it, and then we are going to call this rotate right module inside this test bench, and we are going to then map its output and inputs according to these. And after that, inside this initial block, we are going to say at 0 time make A and B both inputs as zeros, and then after 10 nanoseconds we are going to start this for loop, and we are going to increase the value of A by 4 and the value of B by 1, so that we can check, okay, if we are going to rotate by 1, we are going to say, okay, B is equal to 1. If we are going to rotate the bits by 6, we are going to say B is going to be 6. So we are going to check all these combinations like this. And after the end of this for loop, we are going to make A equal to this and B equal to this, so that we can check our output with the help of more input combinations. So this is our complete test bench code, and we are going to save this as well and compile this. Let's run this test bench. So this is our output according to our inputs. So B input is going to actually give us the values by which we are going to rotate these bits of A signal, and then we are going to check, like for example B is equal to 1 here, so we are going to rotate A by 1 towards the right side. B is equal to 2, we are going to rotate A signal by 2 bits, and same with these combinations. And we can see that once we are going to rotate this A value by 1, we are going to make it to 2. So same way, if we are going to rotate, if the values inside A are 8, if we are going to rotate the bits towards the right side by 2, we are going to get again the 2. So same way these all combinations are going to work. So now I am going to show you one more way using this very low code to do the same stuff. And in order to do that, what we are going to do is we are going to skip out these lines, and we are going to include these three code lines into our code. So uncomment these lines, and in order to use these lines of code, we are going to first of all define these s1 s2 as wires as well at the top, and these s1 s2 wires we are going to use here. And here what we are doing is we are going to apply the same logic but in a short manner, and these three lines actually in future we can use to convert our this behavioral code into a structural model code of Verilog. This code, if you are going to use, you are never going to change your behavioral code into a structural one, but with these three lines, this is just another way of implementing the same stuff, the rotate right logic. So here actually we are checking the first three bits of B and we are going to take some decisions. The logic we already know from this code, and what we are saying is check the first bit of B, and that is B0. If it is going to be 0, then we are going to say okay, don't rotate anything, just assign A to S1. But if it is going to be 1, we are going to say rotate towards right side by 1. That's why we are adding this least significant bit at the most significant bit location, just like we are doing here. This is actually this case. P0 is equal to 1 here, and then we are going to say now use this S1 here, and then we are going to check now P's second bit, and that is B1, and we are going to say now if it is 0, just assign this S1 which we got from here to S2. But if P1 is equal to 1, then we are going to say take the two least significant bits of this S1 and place those at the most significant bits position like this. This is the way we are going to rotate, and this is actually now going to cover these next two combos where B is equal to 1. First two combos are there, this one, right? And then we are going to say now use this S2, and then we are going to say if B2 is equal to 0, just like it was 0 in first four cases, we are going to say, then we are going to say okay, just assign this S2 like this to S. But then we are going to say but if B2, the third bit of B is equal to 1, then we are going to say okay, pick up the first four least significant bits of S2 and place those at the most significant bits position like this. This is the way we are going to rotate, and we are going to implement all these four combinations, last four combinations where B2 is 1. We are going to do this implementation like this. This is actually a very simple way. We can use a flow chart or a flow diagram, and we can check this as well on internet. There you can find some material where you can understand this concept in a better manner. But this is the way we are going to implement this rotate right. And these three lines in future we can use using muxes to convert this behavioral model into a structural model. I am not going to do that today, but I am going to just show you this is the way we can use this behavioral model. So now let's save this and let's compile this. And now let's do simulation once as well so that we know our result is same. It is implementing the rotate right the way we want. So we are going to see the same output which we were seeing previously. So let's end this simulation. So in Verilog, there are these two ways which we can use to implement rotate right using the behavioral model. And now let's flip over to our VHDL project and see how we can implement the same thing using a VHDL code. So now we are inside the VHDL project, and this is the file where I have implemented the VHDL program. Rotate right, it is again of 8 bits, and S is the out vector, and A and B are the in vectors, and all are 8-bit vectors. The entity name is rotate right 8, and then in the architecture of rotate right, we are going to use this code line inside the begin block, and we are going to say okay. Use this rotate right by checking the first 3 bits of B, and whatever value we are going to get, like if we are going to get 1 from here, we are going to rotate A using this ROR by 1, and this ROR we are going to get from here. But remember, this ROR operator they have included in VHDL 2008 only, so you have to click here on this file, go to the properties, and then you are going to click here on VHDL, and here you are going to select this 2008 version. Otherwise your code is not going to compile and it is going to show an error. So remember this step. Now we can use this ROR operator given inside VHDL to implement our rotate right, and then end behavior is architecture. Now let's compile this first and simulate it so that you can see its output. Testbench, simulate. So drag these 3 signals to this wave window and press run. So we are going to see the same simulation result, and we can check here like B is first 1, then 2, then 3, then 4, then 5, then 6, and we are going to rotate the values of A, the bits of A like this. Now let's end this simulation, and I can show you the test bench written in VHDL language as well. The test bench which we are using. So this is the test bench entity, and test bench then architecture behavior of test bench is, and here we are calling this entity rotate right 8, which we defined in our design file, and we are going to use that as a component, and then we are going to define these signals, and here we are going to call that the entity rotate right like this, and we are going to use this port map to map our output and input signals like this. And after that, this process block we are going to start, and in this we are going to first make our 2 inputs as zeros, then wait for 10 nanoseconds, then start this for loop, and we are going to increase the values of A by 4, B by 1, so that we can actually check all rotates according to the values of B, like B 0, B 1, 2, 3, rotate by 3, B is equal to 4, rotate by 4, and wait for 10 nanoseconds and loop, and then we are going to make A and B equal to these values so that we can check more combinations of inputs, and then wait again for 10 nanoseconds. This wait we are going to use because we don't want to run our process for infinite time, and then this end process and then this end architecture we are going to do here. So this is our test bench for our VHDL code. Now let's see what are the other ways which we can use inside VHDL to implement this rotate right. So skip out this line, use this code line. So in this code line actually we are going to use this rotate right function, which we can get from this library numeric underscore std.all. and after that we are going to use these. This code line is also included in this. So two integer function, unsigned function, and b's same first three bits we are going to use to get our values, which are going to tell us that rotate the bits of a by this number. So this is a. So this is the way we are going to use this a and b using these functions. And this is the rotate right function. This is the way we can use this. So let's start the compilation of this modified code. So according to your needs, the way you want to synthesize or do simulations, you can pick any of these behavioral models and they are going to perform the same thing. These simulation results we can use to check that whatever we want to get, we are actually getting that or not. So these are the same outputs and inputs we are going to see. Now let me show you another way. So two ways we have seen in the VHDL. Keep out these lines and now include these code lines. So here we are going to use this procedural assignment using this process block to implement the same logic is going to give us the rotate right of 8 bits. So here again we can either use these two inputs inside the process to run this program, or we can use this process all. So process all is going to automatically check all the input signals and we don't need to write specifically input signals like this. And this process all we can only use once we are going to go to this file and we are going to select from the properties again this VHDL 2008. Since we are already using this, we don't need to worry about. But if your this version is default this version, then you can't use this all keyword as well. So remember this thing. So process all we can use like this, and then we are going to use inside this block the if else statements to implement our logic. So we are going to check the first three bits of our b, and we are going to say if first three bits of b are 000, s is going to be equal to a, no rotation. Else if first three bits of b are 0001, then rotate right is a by 1 and put inside a output. So we are going to place this least significant bit of a at the most significant bit position. Same way, if p2 down to 0 is 010, we are going to rotate by 2 bits our a input, and this is the way we are going to implement. Same way, p is 3, 4, 5, we are going to rotate by 5, p 6, 7, we are going to put here all the combinations, and else we are going to say make output equal to ZZ, and then end if and end process and end architecture of our code. So now let's save and compile this program as well. This is also behavioral modeling using VHDL. Always run and check these signals. Your output is according to your inputs. So we are going to see the same outputs. Now we are going to check a fourth way to implement our rotate right. So we have to skip these gold lines, and that rotate right behavioral model we can actually use to convert our behavioral model into a structural model later. So we are going to modify our behavioral model and we are going to include these gold lines. Uncomment these gold lines, go here and define two more signals which we are going to use. This is the S1 and S2. We are going to use this S1 to implement our one shift or one rotate, and we are going to use this S2 to implement our 2-bit rotation. So first of all we are going to say okay, check this B0 bit, first bit. If it is 0, place this A as it is inside S1. Otherwise, if it is 1, then rotate this by 1. Rotate A by 1 like this. This is the same which we have used here. If this is 1, this bit, least significant bit of P is 1, then place this inside S, right? So first we are going to place this into 1. This is the 1 bit rotation towards the right side. Then we are going to use this S1 and we are going to say now check the second bit B1, and we are going to say if B1 is equal to 0, place S1 as it is into S2. Okay, just like we are going to implement the first two things 0 0 1 and 0 0 0. But we are going to say if now B1 is becoming 1, like this case and this case, then we are going to say these cases 0 and 1 we have already from here. So then we are going to say in the next line if B1 is equal to 1, rotate here S1 by 2. Otherwise, we are going to say if B1 is equal to 0, which is this case, we are going to say put S1 as it is to S2. So this is just the difference, and then we are going to check the third bit, which is B2, and we are going to say if B2 is equal to 0, place S2 as it is to output. So this is going to cover, this S2 is going to cover our first four if statements which we have defined here. First four. Then our B3, B2, the third bit is actually 0 for all the cases. And then we are going to actually say if P2 is becoming 1, then make modification to this S2 and place these first four least significant bits at the last four most significant bits position. So we are going to rotate these most significant 4 bits toward the right side and rotate like this. So just 3 lines. These 3 lines we can actually use later to implement this rotate right as a structural design. But I am not going to show you in this video that thing. But this is just right now a behavioral model, but just in another way. So this is our fourth way we can implement rotate right in VHDL. Compile and again run this simulation by going to Testbench. and we can see the same output here. Rotate right is going on. So let's go and end this simulation. So guys, today actually we have seen the two ways inside Verilog language, the way we can implement our rotate right, and then we have seen four different ways to implement rotate right using behavioral model inside VHDL. So thank you guys. I hope you guys have enjoyed this video. Have fun.